Welcome to The Explainer. Today, we're diving into something absolutely fascinating at the intersection of human biology and cutting-edge machinery. We're going to explore the dual narrative of rehabilitation. On one side, you have the human element, a patient tracking their incredibly grueling recovery on a daily dashboard. And on the other, we're looking under the hood at the engineering blueprint of robotic exoskeletons. These machines are literally changing what it means to relearn how to walk, and it's a wild ride.
So it begs a really bold question. Can we actually engineer a perfect recovery? For decades, regaining mobility after a stroke or a spinal cord injury has relied pretty much entirely on traditional physical therapy, which is an exhaustingly demanding process for everyone involved. But what if we approach human rehabilitation as a design tutorial? What if we could build a machine that solves the physical limitations of traditional therapy, all while maximizing the brain's natural ability to heal? All right. Let's put on our engineering hats for a second and outline the core requirements. If you're tasked with building one of these recovery machines, it's not just about making a cool robot. The blueprint has to ensure absolute patient safety, deliver thousands of high-intensity repetitive steps, and maintain strict mechanical consistency. But on top of that, it has to clear massive clinical benchmarks, actually be financially viable for hospitals, and eventually be lightweight enough to take home. It's like a giant, high-stakes puzzle.
Phase 1. Designing the rehab journey. Balancing the patient's recovery dashboard with the mechanical blueprint.
The baseline design challenge we're facing here is pure human endurance. In a standard clinic, traditional physical therapy exhausts both the patient and the staff, manually supporting their weight, which naturally leads to variable step consistency. Now, it is fantastic for teaching patients adaptive real-world motor control, like catching yourself if you stumble, but on the flip side, robotic exoskeleton systems offer precise mechanical consistency, high-intensity repetition, and a super safe environment to get severely injured patients upright way earlier in their recovery. Both approaches have undeniable merits.
Moving to Phase 2, engineering adaptive control systems, looking under the hood at how exoskeletons adapt to patient needs.
Modern robotic therapy relies on a highly sophisticated engineering loop. You see, early rigid machines basically just forced a patient's legs through a pre-programmed motion. But engineers quickly realized that if the robot does all the work, the patient's brain effectively goes to sleep. So the machine has to adapt. First, it detects the patient's intent to move. Second, it calculates and provides only the minimal necessary assistance. And third, it continuously analyzes the mechanical consistency of that step. This loop is happening hundreds of times a minute.
And the real secret here is this concept, assist as needed, or AAN. These are control algorithms specifically designed to actively minimize the robot's output. Think of it like highly advanced reactive training wheels. If a patient only has 20% of the strength needed to take a step, the robot kicks in exactly 80%. But as the patient gains strength, the robot instantly backs off. AAN ensures you aren't just passively riding the robot, which is absolutely vital for driving long-term neuroplasticity.
Taking that a step further, we have Human in the Loop, or HITL. This is an advanced control strategy where the machine doesn't just look at movement, it's reading real-time physiological feedback. It monitors the user's muscular effort or metabolic cost, creating a truly symbiotic human-robot interface. The machine is constantly adjusting its parameters to make sure the patient is always operating right at the very edge of their physical and cognitive limits.
And when you compare the brain activity data between these methods, the contrast is just stark. Passive robotic guidance is great for preventing muscle atrophy, but it shows minimal activation in the brain's motor cortex. However, active-assisted interactive mode, which requires the patient's actual cognitive effort to trigger the sensors, produces significant, localized hemodynamic activation in the brain. Active effort is literally the secret sauce to actual neural recovery.
Phase 3. The MCID reality check, analyzing the hard data comparing robotic therapy to traditional methods.
To figure out if these complex machines are actually working, clinicians use a metric called the Minimal Clinically Important Difference, or MCID. This isn't just about statistical significance on a spreadsheet. It's asking, does this data translate to a meaningful improvement in daily life? For example, for a stroke survivor, their gait speed needs to increase by about 0.10 to 0.16 meters per second for them to actually notice a difference. Just 0.10 meters per second. But that tiny fraction is the difference between crossing a street safely before the light changes or being completely homebound. That's the ultimate hurdle our engineered system has to clear.
Now, the meta-analytical data comparing robotic exoskeleton gait training to conventional physical therapy reveals a pretty nuanced picture. For raw walking speed on the 10-meter walk test and endurance on the 6-minute walk test, they're basically tied, statistically comparable. There's a definite plateau effect. However, the robotics pull significantly ahead in the timed up and go test, which measures dynamic balance, and the WI-SCI-2, which tracks functional ambulation independence.
For the patient, that functional independence translates perfectly into a personalized dashboard, tracking things like total swing and stance time alongside step length and speed. By monitoring these exact biomechanical data points, both the patient and the therapist can see their long-term recovery metrics improving in real time. It takes what is often a frustratingly slow recovery and transforms it into an objective, totally data-driven journey.
Phase 4, gamifying the blueprint. Using sensor fusion and virtual reality to boost cognitive engagement.
Let's be real. Repetitive clinical therapy can get immensely boring. So to solve that lack of engagement, engineers built an array that can essentially read a patient's mind, detecting their motor intent fractions of a second before a physical movement even occurs. The foundation for this is an integrated sensor fusion system. We're talking inertial measurement units, electromyography sensors picking up muscle electricity, gyroscopes, and load cells planted right under the feet. And when you take all that rich, real-time sensor data and feed it into immersive virtual reality, absolute magic happens. You create a closed cognitive motor loop. Instead of staring at boring clinical ceiling tiles, the patient is suddenly stepping over virtual logs in a digital forest. The robot's mechanical feedback is linked directly to visual and haptic rewards. This gamification keeps the patient highly motivated, and more importantly, it actively drives the neuroplasticity required to make the recovery stick.
Phase 5, analyzing cost and accessibility. The socioeconomic design flaws limiting widespread adoption.
Because despite all the incredible clinical and engineering milestones we've talked about, this blueprint has a massive socioeconomic flaw that's severely limiting equitable access. The acquisition costs are just staggering. We are easily talking over the 6-figure mark per unit. And because it's still considered experimental in many healthcare systems, there's a huge lack of widely accepted insurance reimbursement codes. That completely stalls adoption for your average regional clinic.
It sets up a really tough cost-effectiveness battle for clinics. Heavy robotic exoskeletons require huge upfront costs, expensive maintenance, and usually end up limited to upscale urban hospitals. On the other hand, conventional manual therapy has a much lower upfront equipment cost, but it incurs massive long-term staffing costs and places a tremendous, often injury-inducing physical burden on the physical therapists themselves. The whole industry desperately needs a middle ground. Phase 6. Building hybrid future systems. Moving from rigid clinic systems to lightweight home solutions.
So the future of this tech actually relies on a totally new blueprint. We're seeing a shift away from rigid frames to lightweight, fabric-based, soft exosuits that use cables to assist natural joints. They integrate dynamic body weight support to catch lateral falls and utilize AI and deep learning to constantly adapt the therapy without a clinician even needing to be present. And at the absolute bleeding edge, they're developing brain-computer interfaces which could let patients with severe paralysis command the suit directly by decoding their brainwaves. By closely tracking intricate temporal characteristics, like comparing the delicate balance of single support and swing phases on a patient's affected side versus their unaffected side over time, these future hybrid AI systems will seamlessly translate complex biomechanical feedback into highly personalized home recovery loops. We're talking about sustained, safe therapy right in the patient's own living room.
But honestly, no matter how advanced the AI or the soft robotics get, clinicians are always going to rely on these core objective metrics to evaluate success: velocity, endurance, stability, mobility, and motor impairment. These tests are the anchor. If a brand new home-based soft suit doesn't show sustained improvements across these specific clinical scales, it simply won't be adopted into standard medical practice. Period. Which leaves us with a pretty profound question to ponder as we wrap things up today. Will the future of rehabilitation be driven primarily by the empathetic, highly adaptable hands of a human therapist, or by the tireless, precise execution of adaptive algorithms? The reality is, it's likely going to be a deeply integrated partnership of both. Thank you so much for joining me to explore the incredible engineering behind human recovery. Stay curious, and I'll catch you next time.